Welcome to our second video on our 2-12 lab demo. Again, these help videos here are intended to be sure that you fully understand the energy changes that accompany chemical reactions. You cannot understand chemical reactions unless you have a grounded, stable understanding of the energies involved in every chemical reaction. So today we're going to pick back up on this video with our second demonstration. In the second demonstration, we have acetic acid called vinegar, and they're reacting it in baking soda. The AQ after it means that these are solutions. So we have acetic acid in a solution. And what that means is it's dissolved in the solution. So this substance is broken up. And then we have sodium bicarbonate, also called baking soda, in solution. AQ means it's in solution. So that was put in water as well, and the water pulled it apart. And then we saw a chemical reaction occur. And our product was carbon dioxide gas, water, and a salt that is dissolved called sodium acetate. So when we're looking at this reaction, it looks like the sodium, Na, ends up joining with a new partner. The sodium was with HCO3, and when it's done, it's with C2H3O2. In chemical reactions, what happens is things join up with something different. Now, what happens to the HCO3? What happens to the H? Well, a chemical reaction occurs where we end up with carbon dioxide and water in this particular reaction. This H right here and this H right here join up with one of the O's from CO3. H, and one of the O makes H2O. We lost an O off the CO3. If you take one O off of CO3, you have CO2, and CO2 is a gas. What was the evidence? We saw a gas bubbling and fizzing. That was the CO2 bubbling out of there. We knew it was endothermic. How do they know it was endothermic? There was a temperature drop. The thermometer in there clearly dropped. Energy must have been going into the reaction. The thermometer was in the water. The water was the surroundings. The water is where the chemical reaction was taking place, but energy went from the water into the reaction. The water was the surroundings. The AQ was the surroundings. That was the water that had dissolved this stuff. And the temperature in the water went down, which meant energy was leaving the water to go into the chemical reaction. The reaction was the system. That was the NaHCO3 and the HC2O3. Those were the substances that were reacting. When the temperature went down in the water, it meant it was leaving the water to go into the reaction. Into is what we mean by the word endo means in, such as endoskeleton. We learned earlier that there are two driving forces between when driving a chemical reaction. One is enthalpy, symbolized by delta H. We learned in the previous help video that there are two energy changes in every reaction. The first energy change is breaking apart the reactants. The second energy change is what happens when the products form. Enthalpy refers to the overall energy change. It compares to the energy in, which is used to break the reactants, and the energy out as new bonds form. We know that in the universe, things are tending towards a lower energy. So when we look at number 4, in the universe, chemical reactions are tending towards lower energy or enthalpy. That means the energy out, being released from the reaction, is more than the energy taken in. Things are tending towards a lower energy. When at lower energy means improved stability. The famous trade-off, lowering energy means that that chemical reactions are trying to improve stability. The second factor involved in chemical reaction is entropy. Entropy, as we remember, is symbolized by delta S. Entropy is the amount of disorder. And we know that in the universe, things are tending towards greater disorder. Number 5, increasing entropy. So in the universe, they want a positive delta S. They want a negative delta H. If there's a negative delta H and a positive delta S, the reaction is said to be spontaneous. What do we mean by an increasing entropy or increasing disorder? We mean that large molecules are being broken apart into smaller molecules. We mean that solids are forming liquids or gases. Disorder means that they're free to move around. A big thing breaking up into a lot of small things is greater disorder. Gases and liquids can move around wherever they want. That's greater disorder than a solid. What must be the driving reaction in this particular chemical reaction? Well, we just mentioned that this particular reaction is endothermic. Endothermic means that it really doesn't want to happen regarding enthalpy. So enthalpy must not be the driving force. It must be entropy. So entropy must be increasing. Well, it is. Take a look at this. We have 2 substances in the reactants. We have 3 substances in the product. So the number of things have gone up. These bigger things have broken apart into smaller things. The second thing is we see that we're making a gas. That's greater entropy. So entropy is going up in this reaction, as we have explained right here. Now they're asking us to draw what is occurring in this reaction. They want us to draw what is occurring in this reaction. Make a sketch. Well, here I've got the sketch, make a sketch highlighted in purple. That's because the sketch is in purple. Here's our sketch right here. Down here is where we have the reactants. The line right here, this blue line, this light blue line is the energy of the reactants, and it starts right here. The energy graph is being drawn with this purple line, Here we go. This is the energy we started with. We've got to break up this HCO3. Has to break up. We know this H is coming off and an O is coming off, and it's joining the H over here. This H is joining this H with one of those to make H2O. The CO2 is left. The Na ends up with the C2H3O2. It's a different substance. So we're breaking bonds. To break those bonds, we have to add energy in. This is the energy going in to break it up. When we get to the top of this hill, at this black line, at this black dot, this is where everything is broken up and new bonds can begin forming. So at the top of that steep curve, at the top of this curve, that is where everything is broken up and it's now ready to react. This red line is showing the total energy that went in. So we go from this blue line all the way up to the top of the purple curve, the steepest part of this curve. That was the energy that was put in to break up the reactants. That's the energy, activation energy. This is the energy in. Right here at this black dot, energy begins to be released as new bonds are forming, as we make the CO2 and the H2O, etc. New bonds are forming and energy comes out when bonds form. Energy is needed to break bonds. That's the energy in. But now when new bonds are forming, so energy can come out. This pink line is the energy out. When we compare the energy in arrow, this is the energy that went up and into the reaction, and we compare it to the energy out, we can see that a lot more energy went into this reaction than came out. More went in. When more goes in than came out, it's said to be endothermic. Line 1 is the energy in. Line 2 is the energy out, the pink line. Line 1's bigger than line 2, so more went in than came out. That's what endo means. More went in to break up the reactants than came out. That means that the enthalpy overall must have gone up. The enthalpy increased. The net energy, if we take the length of line 1, the length of the line going up, the length of the line in, and we subtract the length of the line out, this big red line minus this shorter pink line, we can clearly see that the in line is bigger than the out line. More went in is bigger than out, so that is positive. A big number minus a smaller number will result in a positive number. So the enthalpy is positive. A positive triangle H, a positive enthalpy. How big is our enthalpy? Well, here's the energy we started with. This is our initial energy, the blue line. When we're done, the products are on this orange line right here. So the energy went up from here to here. Reactants to products. The products are above the reactants. So there was an increase. That arrow up is showing you the net change. The energy started here. It ended here. Our net change, triangle means change. Our net change is that green line right there. That green arrow up. It went up. It went from a lower level to a higher level. That is energy up. That is an increase. If the up arrow, again, is bigger than the arrow pointing down, it's endothermic. The energy had to go up. The up arrow is bigger than the down arrow, so overall the energy went up. Well, why did this reaction happen? If it is in fact endo, and we know that things do not want to be endo, they want to be exo. In the universe, energy wants to be released, so stability is improved. Why is it endo? Why was it endo? The product must be less stable than the reactants. Why would that ever happen? Why would the stability of the products be less than the stability of the reactants? The reactants are more stable than the products. Why? Because entropy was increased. We ended up with 3 products. 3 types of things were in the products. Only 2 types of substances were in the reactants. So we ended up making more types of things. That's greater disorder. Not only that, one of the products was carbon dioxide. That's greater disorder. So the trade-off here, although the reaction wasn't driven by enthalpy, enthalpy wants it to be minus delta H. It was positive delta H. The entropy was increased. So that is why this second reaction happens. If anybody ever says, why would an endothermic reaction happen if the universe is wanting exo, if the universe is wanting a release of energy to improve stability? Why would that ever happen? To increase the other driving force, which is entropy. Things want chaos. Things want disorder. Big things falling apart into smaller things. Solids reacting with other solids, or liquids reacting with liquids to produce gases. That will also drive a reaction. This concludes our video on Demo 2. We'll finish up with a video on our final demonstrations. One more video on Demo 3 and Demo 4. And we will wrap up 12-2. Thank you for watching.